Chapter 13, we're looking at equilibrium. For most of the chemical reactions we've done, we have run them such that the reactants get completely used up and form products, or so we assume. And examples of that would be when we react zinc with hydrochloric acid, we get hydrogen gas generated along with zinc chloride. Hydrogen and oxygen combine to form water, or silver nitrate precipitates to form silver chloride and sodium nitrate. So those are reactions that go almost to completion or to completion. Some reactions go both ways, however. Sometimes the products, when they're formed, can combine with each other and reverse the reaction to get reactants. An example of this we'll see as a demonstration is nitrogen dioxide dimerizes to form N2O4. The way we can tell this is going on is nitrogen dioxide is a brown gas. You saw that when you were dissolving the silver coins when you reacted it with concentrated nitric acid. N2O4 is a colorless gas, and so when we have both of them in a single container, we can cause the reactant container to either look very pale brown, showing a little bit of nitrogen dioxide, and therefore mostly products, or very dark brown, showing mostly nitrogen dioxide and hardly any product. A dynamic equilibrium is indicating the fact that we have motion going on at a microscopic level. Dynamic means that it's moving, there's not stagnation. Now, if we have a dynamic equilibrium and we look at it with just our eyes, so that's macroscopically, it looks stable. It looks really boring. We can't really see any change going on. However, if we were to look at it at a microscopic, preferably an atomic level, what we would see is motion of the particles combining as reactants to form products, or the products combining, reacting with each other to go backward to form reactants. We have a dynamic equilibrium that exists in a closed system. When we reach equilibrium, the concentration of the reactants, the concentration of the products are constant. They're not necessarily equal, but they are constant. They don't change. So in another way of looking at it, when I reach equilibrium, the concentration of each of these substances doesn't change, but they don't have to be equal to each other. Even though they are reacting between reactants and products, the concentrations don't change. If we look at an example of equilibrium of a phase change, our first container, we have liquid in a sealed container vaporizing. So we have liquid particles leaving the surface, becoming vapor. And as the process continues, as time goes on, what we see are there are some particles of vapor that start condensing. They start going back towards the liquid. And when we reach equilibrium, we have as many particles evaporating. And if we count those up, we have 1, 2, 3, 4, 5, 6 particles shown as evaporating, and that number of particles evaporating is equal to the number of particles condensing. So we have 1, 2, 3, 4, 5, 6 of those condensing. So when my rate of evaporation equals my rate of condensation, then I have equilibrium. If we're to graph this process, what we have are the reaction rates on the vertical axis. We have time on the horizontal axis. And as we see, the forward rate decreases because the rate's going to decrease as the concentration of reactants decreases. And the reverse rate starts out at 0 because I have no products and slowly increases as I get more products. And if I'm going to reach an equilibrium, then what we're going to find is the forward rate of the reaction is equal to the reverse rate of the reaction. When that is true, again, we have a dynamic equilibrium. When we're looking at reactions and we're trying to figure out a value for an equilibrium constant, we're going to look at something called the law of mass action. And we're going to take our generic chemical reaction where we have A moles of A plus B moles of B reacting with C moles of C and D moles of D, and we're going to write it as an equilibrium expression or equilibrium reaction. That's what's there. And the double-headed arrow shows that I have equilibrium going on. The equilibrium expression is this thing right here. K is the equilibrium constant, and sometimes it's written as KEQ. And it is, very simply, the concentration of each product raised to its coefficient. So I have product C raised to C moles. I have product D raised to D moles. However many products I have, I do that in the numerator. In the denominator, it's the number of moles of A is the power of reactant A, and reactant B is raised to the number of moles of reactant B. And so that's my equilibrium expressions. And these are equilibrium concentrations. because I'm finding an equilibrium constant. When we were dealing with kinetics, we were looking at initial concentrations. In this unit, we're looking at equilibrium concentration. I can write the reverse reaction, which is down below here. And so here I have C moles of C and D moles of D going now to A moles of A and B moles of B. So the equilibrium expression is going to look very similar. It's essentially standing it on its head. So we have this time equilibrium constant and with a prime showing that it's different from our original one, in this case reverse. Again, products over reactants raised to their specific number of moles. And it turns out the relationship between K and K prime is this. K prime is equal to 1 over K. So when I reverse a reaction, I take the inverse of the equilibrium constant. And that's something that's actually fairly important to keep in mind. If I take my initial reaction and I multiply it by a coefficient, so in this case X is 2, so I have 2 times A moles of A in my reaction and 2 times B moles of B in my reaction. When I do the equilibrium expression, so I get a new prime indicator. It's related to my original reactions, double prime this time. I'm just going to take both my values here, in this case my entire new coefficient, and that becomes the exponent for each react. And so my value here is K to the X. So K double prime, in this case, equals my original K equilibrium to the X power. So whatever I multiply as through each of my coefficients, that becomes the power that I raised my K value to. Lucky for us, units are not considered. Units were a big deal for K. In kinetics, units are really not a big deal at all, not really even considered for K when I'm looking at equilibrium. The equilibrium constant for any given reaction is the same at a particular temperature for a reaction, and it doesn't matter how much of each substance I start with. So the initial concentrations are not important. So if we look at this table, we have a reaction of nitrogen plus hydrogen, and we're forming ammonia. Here's our table of initial concentrations. So in our first reaction, we start with both reactants and no products. In our second reaction, we start with no reactants and only product. In our third reaction, we start with a different amount of each. We let the reactions run, and then we look at what is the concentration of each species at equilibrium. It doesn't give us a whole lot of information, but if we use these equilibrium concentrations and put it in the equilibrium expression, we'll find the value for the equilibrium constant is the same for reaction 1, reaction 2, and reaction 3. So it doesn't matter what the initial concentrations are. At one temperature value, this is always going to be the case when we reach equilibrium.